One of the biggest complaints that we have when we're working with kinematics is how to get things started. So a lot of times we would say, oh, here's a cliff and here's a ball, and we're going to launch that ball off of the cliff with an initial velocity of 20 meters per second. And the question is always, didn't the ball start with a velocity of 0? How did we actually get it to be 20 meters per second? And we didn't really know how to do that just with kinematics. We don't know how to start things. So now we're going to, since we know how to use Newton's laws, we're going to learn how to launch things. So let's look at a problem like that. Let's just take this problem and let's figure out some launching. So maybe we have, here's a cliff. It's a 5-meter tall cliff, and here's our person is standing up here and they're ready to launch this ball, and they're going to throw it perfectly horizontally off the cliff. And so the question is how does that happen? Well, obviously they apply a force, and so if this is our initial velocity equals 0 situation, sometime later, this person is sort of like really leaned into her throw, and she's like, oh, there's the throw and there's the ball, and we're like here. So what happened is the ball went a certain distance, maybe a delta x is 1.5 meters or something like that while she's throwing. In process, at this point she lets go and the velocity is our 20 meters per second, and then we know obviously that on launch the thing is going to go land over here somewhere, and our typical question is going to be maybe where does this ball land. So the thinking is what if I know these guys, and let's say that this is a ball that has maybe a mass is a half of a kilogram or something like that, a 1-pound ball. How much force is required in order for you to throw that ball like that? Well, so if I'm looking for force, I know according to Newton's law, force equals mass times acceleration. I'm looking for force. I know the mass. I need to know the acceleration in order to do that. So I'm going to start in this case with my variables, v0, va, t, delta x, and I know that I'm starting with an initial velocity of 0, and I'm ending with 20 meters per second, and I'm going to have that distance be 1.5 meters that I'm able to move the ball while I'm throwing it. If I can know these guys, I can actually find the acceleration, right? V squared is v0 squared plus 2a delta x. So that means that the acceleration is v squared minus v0 squared over 2 delta x. So it's going to be 20 squared minus 0 over 2 times 1.5, or 400 over 3, or 133 meters per second squared. Okay, so there's your acceleration. We're going from 0 to 20 meters per second in over a distance of 1.5 meters, and we figure out that has a huge acceleration, 133 meters per second squared. So what does that do for us? Well, I can now go over here, and again, I've got the ball, so I'm going to take this ball and do a free body diagram. What is going on? Well, obviously, gravity is pulling down, mg, but somehow my hand, right, is, I don't know how I'm going to draw this hand, so let's say that my hand is here, right, and I'm going to sort of say there's my hand and put my thumb over here. Okay, so there's that. What's happening? I know that there must be a force forward because I'm accelerating this forward, so there must be a force in this direction, right? That's the force of the hand to accelerate the ball forward. If this was all I was doing, if I was done, then what would that imply? That would imply that, yes, the ball is being pushed forward and the ball is being pulled down by gravity. But I know that in my picture here that you're accelerating the ball completely forward, so there must be also a component of the force of the hand must also be up. Some component has to balance gravity so that those guys end up canceling each other out. So if I have my coordinate system here, x and y, and I end up with some of the forces in the x direction, some of the forces in the y direction. In the y direction, I have force of the hand vertically minus mg has to equal mass times acceleration in the y direction, which I want to be 0. I don't want it to happen. So I know that there must be force of the hand has to equal mg in the y direction. I know that those have to balance out. Okay? But that's actually not what I'm interested in. I'm interested in what is the force of the hand forward. So in this case, boy, this is horrible notation. I should probably say that this is force of the hand vertically, right? And this is going to be force of the hand horizontal, right? It's going forward, and that's it, right? There's nothing else going on there, so that equals mass times acceleration in the x direction. But I just calculated that, right? Mass acceleration in the x direction, so the force of the hand horizontally is going to equal my mass, 0.5 kilograms, times 133 meters per second squared. And so I'm going to end up with 60, let's say 67 newtons. That's going to be the force of my hand horizontally. And up here, if I want to finish this one, that's going to equal 0.5 kilograms times 9.8 meters per second squared. So I'm going to end up with 10 times 5 is 55, 4.9 newtons. Okay, so there they are. Force horizontally and the force vertically. And if the real question was, what is the force that's required to accomplish this situation, then I have to say, well, I've got a horizontal force of 67 newtons, and I've got a vertical force of 4.9 newtons. So I need to say that my net force is going to be, just use Pythagorean, 67 plus 4.9 squared. I'm going to end up with, the force, the net force, or the total force, is going to be 67 squared plus 4.9 squared square root. So that's going to be equal to 67.2 newtons. And the angle, the theta, is going to be, I can do, we'll say like inverse tangent, right, of 4.9 over 67. So inverse tangent of 4.9 over 67, and we end up with a 4.2 degrees angle. Okay, so we've now figured out the net force, right? 67.2 newtons, 4.2 above the angle, that combines so that I can actually balance gravity and still accelerate forward with a simple force. Okay, so if the original question, right, maybe it was something about x, but it turns out that I'm interested really in what is the size and direction of the force to cause our starting conditions, right? This is always the problem we had. How do we get to 20 meters per second? How do we get to 20 meters per second? Now we know. We know we have to have a certain force, 67 newtons, 4.2 degrees above the horizontal, in order to apply that to the ball to balance gravity, to accelerate it so that I can go from 0 to 20 meters per second over 1.5 meters. And now I can start my problem, which is with my old school kinematics problem. So that's how the problem's going to work, and we'll go from there.